Hello, in this series of lectures, I typically try to make a connection between RF design on one hand and millimeter wave design on the other hand. And this, I will try to explain that on all the different lectures that I'm going to cover. So, of course, I will talk about some of the fundamentals and then talk about CMOS. There's a very strong focus on silicon and CMOS, although I will also briefly mention gallium arsenide and indium phosphide and show some amplifiers that we made in these technologies. Broadband low loss tuning and matching techniques, power amplifiers, layout extractions, and so on. And so one of the key points for me is to explain to you with very simple examples how things are different at millimeter wave compared to RF, and why some solutions that we typically use at RF are not very well suited at millimeter wave, and vice versa. And just if you think about it, if you would design a very simple amplifier, like a two-stage amplifier, we have a first stage over here, typically millimeter wave or RF circuits are fairly simple. But the devil is always in the details. So we have a two-stage amplifier. I can connect the output of one stage, obviously, to the input of the second stage, just like that. I have to provide some biasing. I can do that with a resistor, or this would be a bias voltage, and so on. And this would be, you could wonder what's wrong with this. Why don't we use this at higher frequencies? Well, what I'm doing here with this inductor, I'm basically tuning out all the capacitors that I have, a capacitor here and a capacitor over there. So I'm just using tuning. I'm not doing any matching. And that's typically what people would do at RF frequencies, let's say below 10, 20 gigahertz. Whereas if you go to much higher frequencies, we follow, or another approach is typically followed, where you have a first stage, and again our second stage, and they can have different sizes depending on whether we want to maximize the gain, the output power, or minimize the noise. And in between I can put a matching network, and matching networks are interesting. They do consume quite a lot of area, so you have to be careful with that constraint, but they are interesting because a matching network or an impedance transformation network gives you voltage gain. Obviously it doesn't give you power gain, it actually gives you a little bit of power loss. But the nice thing about a matching network or about an impedance transformation network, just think of a transformer, for example, you can have voltage gain. So we're going to have a higher gate source voltage. I should write it with small letters here, VGS, higher AC voltage at the second stage. That's the benefit. And then that would be the argument to use a matching network. So RF, typically we just use tuning. Millimeter wave, we use matching. And also to calculate the Fmax of a technology, Fmax assumes that we do power matching, and that would be the definition of Fmax, where the frequency where we still have some power gain after doing what's called complex conjugate matching. So why don't we do matching at RF? Well, if you think about it, if you try to do matching, one of the challenges is going to be how to bridge the output impedance. So let me just draw a very simple small signal circuit here of a transistor. There we go. And this would be RDS. And then we have the input of the second transistor. There we go. So I'm just drawing a very simple small signal equivalent circuit. I should draw it here as well, of a first stage and a second stage. Oh, I have to make myself a bit smaller here. There we go. So we have two GMs, and this is the gate resistance of the gate electrode. This is CGS, this is CDS. Just for my convenience, I'm skipping the gate drain capacitance, or I'm assuming I've unilateralized the device, also something that we're going to talk about in the course. So what do we have now? We have a gate resistance here, which is maybe only like, let's say 10 ohms. And we have an RDS over here, which is maybe 500 ohms. And we need to put a matching network here in between that creates a complex conjugate match for the output impedance of the first stage towards the input impedance of the second stage. Now, to think about it, it's easier to convert this network into a parallel network. You can always do that. You can always do that. At one specific frequency, it's possible, but at any frequency, it's possible to convert a series RC into a parallel RC. So here we have the gate resistance, but now in parallel form, and here we have CGS now in parallel form. Now, if you do that, this resistor here becomes heavily frequency dependent. Now, I should mention that this resistor and that resistor, they are also slightly frequency dependent, but not that much. But if you go from a series RC into a parallel RC network, then you have a huge dependency, a huge frequency dependent resistor. So let's have a look, and we are going to have a much closer look on this during the course. But if you look at versus frequency, and you have RDS on one hand, this resistor RDS, that is, let's assume it's not it's very slightly frequency dependent, and we have a value of around 500 ohms. And then we have that RG. RG is very small, only 10, maybe 20 ohm, depending heavily on the layout and on how you draw it. But if you convert it into an equivalent parallel network, you get something like this. Here we go. Here we go. Now, surprisingly, this frequency here, where they both cross, obviously heavily depending on the technology, the layout and so on, but in 28 nanometer CMOS, for average device sizes, this turns out to be around 140 gigahertz. Can be anything between 140 or 100 to maybe 180 gigahertz. But we have seen various typical situations where this is 140 gigahertz, which is great, because that means that I don't have to do anything special to create complex conjugate matching. If I connect them together and I tune them out, then the tuning or complex conjugate matching is going to give me the same result. And I can just put a one-to-one transformer between the drain of the first stage and the gate of the second stage, and you're going to have complex conjugate matching. But over here, the difference between the parallel gate resistance and the parallel output resistance is huge. It's too large. The difference is too large. And why is this a problem? Well, you're going to have two important problems with that. The first one is loss. A matching network has a power loss, and that power loss typically becomes larger if you need to bridge a larger distance in ohms. So if you have to go from 500 ohm to maybe a few hundred kilo ohm, forget it. It's not going to work. So you could try to do it, but you're going to insert so much loss that it doesn't make any sense anymore to do complex conjugate matching at RF. And a second constraint is bandwidth. I mean, the higher the distance in ohms that you try to bridge on a Smith chart, for example. You can also visualize this nicely on a Smith chart. Also something that we're going to cover during the course. But the problem if those impedances are too far away from each other is bandwidth. So these are two reasons why nobody is using complex conjugate matching at RF frequencies, but we are using it extensively at millimeter wave frequencies. And I would say the crossing frequency is somewhere around 10, 20, 30 gigahertz. And that's actually also something that we simulated. And this is just a figure that I would use during the course. What I'm showing here is the three situations. The first one here is you don't do any complex conjugate matching at all. You just do tuning. And then that's the normalized case, basically. How much gate source voltage do we have in the second stage if we just connect two transistors to each other and you do tuning? At a certain point over here, you see a roll-off, and that's just coming from the RC, the gate resistance at CGS effect. That happens at close to 100 gigahertz. If you do perfect, lossless, complex conjugate matching, you would have huge benefits. Here, I'm assuming I don't have a problem with stability, right? Because complex conjugate matching, you can only do that if you're not limited by stability. And then, of course, you would have if you could make ideal transformers and if you have the area to implement them, then at 1 or 10 gigahertz, you would have huge gain benefits in voltage gain. But these networks, they need to bridge a distance in ohms of several hundred kilo ohms, right? And there's too much loss. And that's the blue line that you see over here. This blue line, here we go, shows you for a practical situation, how much voltage gain do you get? And you see that as we go from a high frequency to low frequency, indeed, initially there is some improvement, but at a certain point, the loss of the matching network becomes so large that it doesn't make sense anymore. And this is now, of course, this is all depending a little bit on the technology, on the device sizes and so on. But this is, for this specific case, around 10 gigahertz. So that's the reason why I typically say 20, 30 gigahertz, those are the frequencies at which it becomes useful to do some sort of power matching. And power matching will then also give you higher voltage gain. Of course, I'm going to talk about other things as well. We talked about bandwidth. Bandwidth is typically related with Q factor. We have seen that the input impedance is an RC of a transistor. Output impedance is also an RC. And you would have to look at the so-called Bode-Fano limit. Bode-Fano limit tells you if you have a certain RC, resistor and capacitor, what is the bandwidth you can get. And there is a Q factor, an RC product on the input side. There is a Q factor on the output side. Which one limits your bandwidth? And also here there is a crossing frequency. At lower frequencies, we typically see that the bandwidth you can get if you do matching is limited on the input side. At higher frequencies, we typically see that the bandwidth that you can get is limited on the output side. Remember that on the input side, we have a series RC. On the output side, we have a parallel RC. And they have a different behavior. And why is this important? Well, everybody is always saying, let's go to higher frequencies because that's where we have so much bandwidth available. And that is true if you look at the spectrum. From a spectrum perspective, there is a huge amount of bandwidth available at higher frequencies. But from a circuit perspective, this is not the case. This is not the case because if you convert these Q factors into an available bandwidth, for example, if you do a fourth order Chebyshev, why a fourth order Chebyshev? Well, we will see in the course that a fourth order Chebyshev, if you use a transformer and you put a capacitor on the input, a capacitor on the output, a resistor on the output, a resistor on the input, this is actually a fourth order network, and you can choose the L's and the C's and the R's in such a way that you have, for example, a Chebyshev approximation, but you can also go for a Bessel or a Butterworth if you want. But you see that at a certain frequency, the circuit bandwidth does not further improve. And that's limited by the quality factor, the Q factor, or the RC product, I should say, on the output of the transistor. So yes, going to high frequencies gives me higher bandwidth, circuit bandwidth, but around 140 gigahertz, things are no longer improving. And going to 200, 300, 400 gigahertz, it makes sense, maybe it makes sense, I should say, from a spectral viewpoint, because that's where we have huge amounts of bandwidth available, but it wouldn't really make sense from a circuit perspective. We don't have the circuit bandwidth available over there. And you can say, well, instead of a fourth order, why don't you go to higher order matching? You can do that, but remember, the limit is there, the Bode-Fano limit. And the Bode-Fano limit tells you exactly the same. There is a maximum bandwidth that you can get from a transistor. Again, these fundamentals is what we are going to discuss during this course, and we are always making the link between RF versus millimeter wave. The same with quality factors, the same with layout. I will show many layouts during the course with inductors. I mean, why do we put so many inductors here on top of a transformer? This has to do with imbalance. This has to do with stability, quality factor, the influence of a center tap of a transformer, and so on and so on. All these things are slightly different at RF versus millimeter wave. And making that connection really helps you in understanding the fundamentals.